Hi, my name is Connor Bush, and today I'm going to talk about a closed system and the relationship between pressure, volume, and everything that relates kind of to the ideal gas law. So here we have a two-part problem. We have a container with a volume of 0.01 meters cubed, and it has 1 kilogram of liquid water and air, and the initial pressure is 101,325 pascals at 298 Kelvin as the initial temperature. It's asking for us to find the final temperature at the final pressure of 200,000 pascals. So we are going to first go here and start looking at some equations. So we have this closed system here. There's water, there's 1 kilogram of water. We know the total volume is 0.01 meters cubed. Our initial temperature is 298 Kelvin. We don't know our final temperature. Our initial pressure is 101,325 pascals, and our final pressure is 200,000 pascals. So we can first look at the partial pressures. So the initial pressure equals the pressure of the water plus the pressure of the air. We can find the partial pressure of the water with a module in Python using the density and or vapor pressure, my bad. So our one unknown in this equation right now is the pressure of air. We can use our ideal gas law to find that. So PV equals nRT. So the pressure of air equals the moles of air times our gas constant times the initial temperature divided by the volume of the vapor phase. So we know that the total volume is 0.01 meters cubed, and that is including the volume of the water plus the volume of the vapor phase. We don't know the volume of the water, but we can find that using the mass and the density, and we can use the density found in Python using a module, which we will talk about later. So the volume of the vapor phase equals the total volume minus the mass of the water divided by the density of water, because the density of water equals mass over volume. So we can substitute this equation here into our pressure of air equation. So we get that the pressure of air equals the moles of air times our gas constant times our initial temperature times the total volume minus the mass of the water divided by the density of the water. And then we can put this equation into our partial pressures equation, because we need to find the moles of air now, because that's our only unknown. So our initial pressure minus the pressure of the water equals the moles of the air times our gas constant times our initial temperature divided by our total volume minus the volume of the water, which we use as substitution here. And then we can get the moles of the air by itself with some algebra. So we have that there. So we can start setting up some equations in Python. So I will make this a little smaller and put this up near myself and keep this information here. So we're going to use Colaboratory. This is we're importing a module here with some chemical engineering tools and data. The data here includes all different kinds of compounds, including water, which we are going to focus on. And it also includes different kinds of tools, and we're going to be using one of these to be able to find different aspects of of the water. So let's start by importing the tools from that module. We'll call that CHE. And then we also need to use the root calculator so we can find our unknowns. So from scipy dot optimize import root. So now that we have that, we're going to initialize that we want water to be our focus. So we can say p equals che.props, and then we're going to specify water here. And the cool thing about this is that we can substitute this for any sort of compound within this toolset and dataset with different compounds. So let's start initializing some variables based off what we have. So we have the total volume, and that equals 0.01, and that is in meters cubed. Our initial temperature is 298 Kelvin. Our final temperature is unknown, so we can't put that here. Our initial pressure is 101.325, and that's pascals. Our final pressure is 200,000 pascals. Our gas constant is 8.314. That's in joules per mole Kelvin. Let me just confirm. Yes. Awesome. So do we have any others that we need? 1, 2, 3. Oh, the mass of our water initially is 1 kilogram. So we can put in this equation for the moles of air. We'll call it N air as we have on the iPad, and this equals our initial pressure minus the pressure of water, which we can use with this tool, PVAP, and then we have it at our initial temperature. This is going to be multiplied by the total volume subtracted by the mass of the water divided by the density of water, which we can do here. And this is all going to be divided by the gas constant times the initial temperature. So let's see how many moles of air we're working with. About 0.356 moles of air. Okay, so now we can kind of start making a function. So we're going to define our pressure function. We'll just call it PQ with parameter x. Our unknown is our final temperature. So we're going to put it into this format because that's more friendly for the root calculator. So the volume of the vapor phase equals the total volume minus the mass of the water initially divided by the density of water at our final temperature. Next, we're going to say that the pressure of water we can get here by saying P that at our final temperature, and that our moles, our pressure of air equals the moles of air. So the pressure of air equals the moles of air times the gas constant R times our final temperature divided by the volume of the vapor phase, which we can just keep because we defined it here. And then we want this to return an equation equal to 0, so we're going to use the partial pressure. So instead of the initial pressure, we're going to have the final pressure because we're going to look at the final temperature, equals the partial pressure of water plus the partial pressure of air. So we want to say that the partial pressure of water plus the partial pressure of air minus the final pressure, and that equals 0. So if we look at our root calculator, we have to have an initial guess, so we'll just guess our initial temperature. It was a success, so our final temperature is around 366 Kelvin. So we can keep that there. So now that we have our first problem figured out with this root, we can look at our second problem, and it's essentially the same idea, except for we're going to have two unknowns. We have our final temperature is going to be unknown, and now our final volume. We know that 0.3 moles of water vapor is going to be desired, and we're going to have the same final pressure. So we can look at our function here and copy this down. I'm going to add a code here and establish that the number of water desired is going to be 0.3 moles. We're going to call this our second function, just add a 2. And then we're going to have to add a second variable that is unknown. So the biggest thing will be having to modify this part, because we need to take into account that the number of moles of the water vapor are going to be coming out of this. So essentially what we're going to be doing is subtracting that by the number of desired moles, but we need to multiply this by the molecular weight of water and then divide this by 1,000, because we need that in kilograms. So this is essentially still mass over density, which is volume. And then finally we need to consider the equation for the water vapor moles. So it essentially should be this, but the moles of the equation for it would be the pressure of the water times the volume of the vapor, because we're looking at the water vapor, divided by our gas constant R times our final temperature. And we want this to return two equations because we have two unknowns. So our second equation would be that the moles of the water vapor equals the moles of the desired water vapor. So we can simply do it like this. And then now we have our second function. To finally get the roots of this, we need to have two initial guesses. So since the parameters are similar to our first problem, I'm going to put in 360 for the first unknown, which would be the final temperature. And then for our second, I'll put in 0.01 for the total volume, excuse me. And then now we can see how this looks. I want to make sure that I have my parentheses correct. Just caught that right there. So it looks like our final temperature is around 370 Kelvin, and our total volume is similar to our first one at 0.011 meters cubed. So that's kind of a basic rundown of pressure, volume, different parameters with the ideal gas law within a closed system. So thank you.